Hello and welcome. In this video, we will discuss how to set up and use several of the Genesys filter synthesis tools. We'll start with passive filter for lumped network filter structures, then M filter for distributed network filter structures, and then finally S filter, a true synthesis tool allowing multiple circuit realizations and providing numerous network transforms and simplification. Okay, let's start with passive filter synthesis tool. Go to the workspace tree and select synthesis, add passive, and we have the option to either select the factory default or the last values we used. I'll press OK, and here you see the last filter actually that was synthesized with this. You see there's a display, a graph, that mimics the simulation of this filter as well as the schematic. And here we can set the topology in the first tab. We can select the type, such as low pass, high pass, band reject. The shape is either Chevy-Chef, Butterworth, Bessel, and then we have a number of others, including user-defined filters. If we browse the list that's available, we can see there's a number of Cower as well as Bessels listed here, and you can define your own filter shape too. You also see Cowers for single-ended. Minimum inductor just minimizes the number of inductors versus capacitors. If you select the differential box, you get a differential filter network. So again, here we can select the a high pass. You notice how the graph changes instantly as well as the schematic. And we've changed the minimum capacitor. Here we change it to band pass. And some of the warning boxes indicate that some filter types are not amenable to whatever bandwidth you choose. In other words, some filters are wide band type filters, some are narrow band filters, and passive tool will alert you to that if you pick a different topology. So we'll go back to the low pass, and next what I'd like to do is show you the settings. From the settings tab, this is where we select the port impedances as well as the cutoff frequency, the order of our filter. In this case it's 7. We're going to change that to 5, and then the attenuation and cutoff in this case. Some filter structures give you more options to select, but you see as we change that, we have an immediate change in our graph and schematic. Here on defaults, we can select the Q for the inductor or capacitor, and here are the G values if you're interested in those. So within just a few button clicks, we have generated a passive network. Okay, next I'd like to show you how we start and use M filter. From the workspace tree, we'll select synthesis, then add microwave filter. In this case, I'm going to select the factory default, which turns out to be a low-pass step filter. And as I step through these, you can see the various configurations. We can select low-pass, high-pass, band-pass, and so forth, just like in the passive case. And there's different shape factors. I'm going to select the band-pass for this example, Butterworth, and not a step or one of these others. I'm going to select the interdigital for our example. And you see it immediately appears as well as the graph. I'll go to the settings, and I'm going to set the order of our filter to 5, and I'm going to accept the default bandpass characteristics. That's 2 to 2.5 gigahertz, and I'll also accept the default resonator impedance. You see when I deselect tap, we now have coupled end on our filter as opposed to tap. Tap works out better when you have broadband filters. We'll create a layout in the options tab, and then we're going to set the manufacturing process. That is how we realize this filter. You see we have a number of processes available. We're going to select the microstrip standard, but unfortunately we don't have a substrate. So I'm going to cancel out of this, and let's get a substrate into our workspace. I'll do that going over to the workspace tree and then add substrate, and I'll copy an FR4 file over, and we're going to use FR4 for this example. I'll go back to the process and click on microstrip, and now we see our substrate is listed here. I'll press OK, and when I do, then Genesys converts this ideal line into microstrip line, as you see here in the schematic. Also notice our graph is distorted. It's off center. We're going to optimize that, but I'm going to change the goals here. Instead of 30 dB, I'm going to make it 20 because in reality, a 5-pole filter wouldn't be able to match that 30 dB spec. So we'll change it to 20, press OK, and then I'll hit optimize on our properties dialog for M filter. And here you see as it progresses, you can see that it recenters our filter as well as optimizes the responses that we asked it to. So I'm going to just run this for a few seconds here and then stop it. It might be some slight improvement later, but for example, this is good enough, I think. So here you see the final response after optimization. If I click on the response, you see we got about a 1.3 dB insertion loss mid-band, as we might expect for microstrip. We'll close this out so we can look at the layout that was automatically generated for us. I'm going to press Control A, and then I'm going to connect all the parts. So now we're ready to do a momentum simulation if we want to verify it. Once we're happy with our layout, then we can export it. And we can select a number of methods, GS2 or Gerber, DXF, or whatever. Lastly, we will look at S-Filter tool. S-Filter offers the additional capability to set zeros of transmission, add transforms like Norton and Kuroda, and filters may be realized as lumped or distributed equivalents. If we go to the workspace tree and select Run S-Filter, here you see the dialog for S-Filter and the specifications page. Let's go to the Start tab. And here we can start a new filter. We can load an existing filter that we've designed. Of course, we can save the settings, and then we can offer the shape wizard, which allows us to start from a known shape, such as Butterworth, Chebyshev, and so forth. It allows us to set the order, upper and lower cutoff frequencies, and so forth. We're going to start from the specifications. In this case, we'll select 50 ohms for both load and source. We can change those. Also, quarter wavelength if we're using distributed network. The shape, whether it's equal, ripple, or flat, high, low pass, band pass, so forth. We can even select the cues of our elements. What I'm going to do is set 3 zeros at infinity, and that gives us a basic low pass filter shape, as you see here, as well as on the graph. What I can additionally do in S-Filter is set zeros of transmission at arbitrary frequencies. So I'm going to select 125 megahertz and set a 0 at that point. When I do, you see the schematic changes as well as the graph updates. And you see our 0 of transmission there at 125. Let's add another 0, let's say at 160 megahertz. When I do, the topology changes as well as the graph. It reflects the new 0. Let's go to this to the load, and let's change the load from 50 ohms to 200 ohms. And when I do that, you'll see that the schematic changes and it adds a transformer. We'll get rid of that later, but the schematic updates immediately, and then of course the graph too. Let's go to Extractions tab. You'll notice there are 20 permutations. And what that means is that you have 20 different topologies that can be realized to express the same response. And the difference is based on the number of caps and inductors and how they're placed in the circuit. So if we were to step through those, we could see basically it would be the same response for any of those permutations. It's just the topology changes slightly, and one might be better for your purposes than another. So let's get rid of that transformer at the output. You'll notice there are a number of transform operations available in the Transforms tab. We're going to select the transformer operation, and as I shift through each one of these options, you can see what happens at the output. You see the 2 schematics there that represent the transform that occurs. Here we're going to absorb that transformer into this T network. I'll select the transformer, and then I'll apply that transform, and you see the transformer has been absorbed into our network, but we still have the same response. Under specification, or excuse me, extractions, we could change the topology, and we do change the topology. The transformer is absorbed just as in the first example. As a final example, I wanted to show you a bandpass filter that was generated with S-Filter, a 60 to 80 megahertz bandpass. And in this case, we've added 2 zeros of transmission, one at 20 megahertz and one at 120. So you can custom tailor your design in order to meet the requirements, let's say, for notching out adjacent channels or interfering channels. And in this case, we've also did a transform to absorb the load, or excuse me, the transformer into our design. As a final thought, the filter synthesis tools in Genesys will help speed your design flow and provide accurate and extensive filter design capability without the need of a specialist. I thank you for watching.